Hi, welcome to video 17, which is all about the inverse of a matrix. So today we're going to define what the inverse of a matrix is and explore some rudimentary attempts at finding it. So to start out with, we're going to begin with a lemma. A lemma is just a fancy way of saying helper theorem. So it is a theorem, but its main purpose is to help us prove another theorem. So this is what we're going to begin with. So this lemma says we've got an m by n matrix A, and we're going to say we've got two identities. We've got the n by n identity matrix and the m by m identity matrix. And what this lemma says is that if I multiply A by the n by n identity, I get A back. Or if I multiply A by the m by m identity, I get A back. Notice we have to have both because A may not be a square, and so the dimensions may be different if we're multiplying on the left or on the right. So we're going to prove this theorem. We're going to show this first bit. The A times In is A. The proof for the other one, IMA is A, is super similar. So we're just going to do one direction for this one. So we're going to start out by starting with this left-hand side, A times In, because that's one we can mess with, right? Can't mess too much with A. And as we've been doing often in our proofs, let's write this in terms of its ijth elements. And ultimately, our goal is to show that the ijth element of this product will be the same as the ijth element of A. So this is going to be Aij times, and I'm going to use the Kronecker symbol here, delta ij. Remember that the Kronecker symbol is going to be 0 if I and j are different, and 1 if I and j are the same. That's because our identity matrix had zeros everywhere except for along that mean diagonal when the row and columns were the same. So since we have a product here of matrices, let's multiply them. So this is going to be the matrix whose entries are the sum over k. And now remember, we pulled the I from A. That sounds painful. So we're going to pull the I from A. And then we have K. And now we're going to have delta K J. So we need the K's in the middle here to be the same. And there's our I and our J. Now to help us see a little bit what's going on here, I'm going to expand this sum for us. So this is going to be AI1 delta 1J plus AI2 delta 2J. Yeah, my cat's chiming in. Plus, and we're going to go up to Aij delta JJ. And then we're going to go up to the very end, which is AIN delta NJ. Now you might be wondering, okay, Professor Ed, why did we write this out? We have this nice concise notation here, right? Well, I wanted to write it out so we could talk about each of these elements and what that product is going to be. So, and specifically why I picked to point out this place when K is equal to J. So this is because, let's say, I'm just going to do a hypothetical here to help us make sense of this, right? So if, now let's say this is my hypothetical board. I'm going to draw a line so I know where to stop. Yeah, that's good enough. Okay, so let's say I, just so we know where we're at, is 2, J is 4, and K is 5, or N is 5, let's say. So we have an idea of what this is looking like. So this would mean if I have the sum over K of AIK delta KJ, this is going to be well, I'll rewrite it with the K and the J in place. Okay, so we have our A 2K and delta K4. And we go from K up, and we go from 1 up until 5 here. So what this is going to give us is I get A 21 delta 14 plus A 22 delta 24 plus A 23 delta 34 plus A24 delta 44 plus A25 delta 54. So this is what that sum would look like for these specific values. And I wanted to use specific values because remember that the Kronecker symbol is equal to 0 if I and j are different, and 1 if I and j are the same. So if I look at what's happening here, here in particular, k and j are different, right? So this is going to be 0, and anything times 0 is 0. So then this piece is also going to be 0 because they're not the same. Same thing here. Here, we're going to get 1. So this piece is going to remain. And then this one is going to be 0, so it goes away. So in the end, this particular sum is going to equal A24 delta 44. But delta 44 is 1, right? Because the subscripts are the same, which means we just get A24. So hearkening back to our IJ notation, 2 was I and 4 was J. So this is going to be AIJ. So bringing this back to what we're doing in our proof. So here, whenever the K and the J are different, those pieces are going to vanish because the delta IJ is going to be, delta KJ, sorry, is going to be 0. And wherever we have delta JJ, it's going to be the same, or it's going to stay because delta JJ is 1. And not only will it be the same, but it's just going to be AIJ. So this sum, even though it looks gross, is just equal to AIJ. Oh, and that's A. Right? That's where we want it to be. So as I went through my proof, I didn't write down my reasons, so let's make sure we do that. So here we have this is because of notation. From this line to this one, we just use the definition of matrix multiplication. Here we just expanded the sum, so that's just using the summation notation. So I'm just going to do a little arrow here because I'm out of space. For this one, the explanation could be that delta KJ equals 0 for K not equal to J. And so delta JJ is equal to 1. And then my explanation for this last line is the definition of A. Since that's just our notation here. So when you go to prove the other direction, that I sub m times A is A, again, this process is very similar. The only difference is these are commuted, but the definition of the Kronecker symbol remains the same. So you're still going to get this situation where everything vanishes except for AIJ. So I'll let you do the proof of the other side. For now, we're going to move into a definition. All right, next we have a definition followed by a theorem. So let's state both of those. We're going to say that an n by n matrix A has an inverse and it's going to look like A to the minus 1. So it looks very similar to our inverse notation for like functions and stuff. If and only if, so I'm going to abbreviate that with 2 F's. So IFF means if and only if. A inverse equals IN equals A inverse A. In this case, we say A is invertible. So we've defined 2 terms in this definition. We've got inverse as well as invertible. So So basically, it's our multiplicative inverse for a matrix, right? So if I multiply a matrix by its inverse, I get the identity. And it doesn't matter whether that multiplication happens from the right or from the left, I'm still going to get the identity. So built up into this definition of the inverse of a matrix is that the multiplication has to commute. A inverse is the same as A inverse A. If it doesn't commute, then we're not an inverse. Also, for this definition, we're dealing purely with square matrices. This is because if I had a matrix that wasn't a square, to find the inverse, it would have to have different dimensions, whether I was multiplying from the left or from the right. So if you feel like exploring the whole world of left inverse and right inverse, feel free to do so. In this course, we're going to stick only to square matrices and their inverses, just to keep it as basic as possible. Okay, so I promised you a definition and a theorem. So we're going to state theorem number 7 now on the board. States, if A is an n by n matrix, so that A inverse exists, and if AB equals IN equals BA, then B is equal to A inverse. So what this theorem is telling us is that the inverse of a matrix is unique. So if I find an inverse for a matrix and you find an inverse for the same matrix, then our two inverses have to be the same. So that's what it's saying here, that B has to equal A if B is satisfying the conditions for the matrix. So since we took the care to create a lemma to help us prove this theorem, why don't we prove that theorem now? So this is going to be an example, and we're going to prove theorem 7, and we'll see where the lemma jumps in to help us out. All right, so we're going to start out by just a reminder, this is what we're trying to prove. So we're trying to prove if we have this relationship, then B is going to be the same as the inverse of A. So we're going to start out with, this is what we're trying to show. So we start out with one of the two sides. Now, both sides of this equation are pretty simple. So I'm going to start with A inverse just because it looks a little bit fancier than B. So we're going to start out with A inverse. Now, to do this proof, we need something else, right? We need something that we can do to try and transform this into B. So to help us out here, let's see what we know. So the information that we know is that AB and BA are related to the multiplicative identity. So if I want to transform from being in terms of A, or particularly A inverse, it would be helpful if I could introduce the identity a little bit, because the identity here can be written in terms of either AB or BA, and that's how we can introduce B into this whole situation. So here's where our lemma comes into play. So I'm going to say that A inverse is the same as A inverse times IN, and this is from our lemma. The lemma told us that if I multiply by an identity, then I don't change the matrix. So now that I've got the identity in play, I can use either the fact that IN is AB or that it's BA to help me introduce B into this equation. Now, I could have put IN A inverse. In this case, I happen to put the IN after A inverse. It doesn't matter, you can work the proof either way. What's important is which of these two I choose to use. My goal is to get B alone. So my goal is to get rid of A from the equation. So because I have an A inverse on the left, if I were to multiply A inverse by A, that would turn into the identity because that's the definition of the inverse. So I'm going to choose the definition of IN that has the A on the left. So this is going to become A inverse AB. And that's by our given information. Now, since we're writing a proof, we don't want to be too hasty with our notation. We want to take it carefully. So what I would like to do is, instead of having the A and B groups together, I want the A and the A inverse groups together. We can do that because matrix multiplication is associative. It's not commutative, but it's associative. So we can regroup to get A inverse A times B, and that's the associative property. Now, A inverse times A is the same as the identity. And that's by definition of A inverse. And to finish, we now have an identity times B, but we know that this is going to be the same as just B for the same reason that we knew that A inverse was the same as A inverse times the identity. It's because of that lemma we proved earlier. So there we have it. If this condition is met, then we can prove that B and A inverse are going to be the same. So now that we've proven that the inverse is unique, assuming there is one for a matrix, it has a unique inverse. How do we find one? Well, let's try. Let's try small. We'll start out small, see what we get. We'll start out with a 2x2 matrix and try and find its inverse if it has one. For example, 33, we're going to determine the inverse of M if it exists for this matrix here. Just a basic 2x2 matrix, easy numbers, 2s and 1s should be nice, right? So what we're going to do to start out on this example is we're going to develop a method. So if you want to just kind of sit back and absorb in and process where this method comes from right now, that's fine. Once we develop it, we're just going to apply it. But it is going to take a little bit of work for us to develop this technique. So if you want to, you can copy this down, or you can just kind of sit back and don't totally relax, because you want to be processing where this methodology came from and why we're going to be doing what we do moving into the future. So to begin with, if I have an inverse, that would mean that M times its inverse is going to equal the identity. In this case, because M is 2x2, the 2x2 identity matrix. So if I were to write this out, this would look like 2, -1, 1, 1. Now, I don't know what M inverse is, so I need some generic representation of it, right? So let's say I use A, B, C, D. And that's going to equal 1, 0, 0, 1. Now, in order for this product to equal this, we know that each of the coordinates have to be equal. So if I find this product here, I'm going to get 2A plus C has to equal this top coordinate of 1. Similarly, I know that -A plus C is going to have to equal 0. I also know that 2B plus D has to equal 0. And I have here that -B plus D has to equal 1. So by using my multiplication, I can derive this system of 4 equations, right, with 4 unknowns. But I wrote them this way particularly because I noticed ahead of time when I was working through this, that these 2 equations only have A's and C's, and these 2 equations only have B's and D's. What that means for us is, instead of thinking of this as one system with 4 variables, we could alternately, that's a word, we can alternately think of it as a system of 2 equations, of 2 unknowns. So they're a little bit simpler. So this system of 2 equations can be rewritten in matrix form as 2, -1, 1, 1, and augment it with 1, 0. And this matrix, or this system, can be written as 2, -1, 1, 1, 0, 1. So now, instead of a big 4x4 system to solve, we have two 2x2s, right? Well, 2x3s if we count the augment. So we could row reduce this one and solve it, and we can row reduce this one and solve it. However, it gets even better than all that. Notice that for these two systems, they have the same coefficient matrix. They have 2, 1, and then they have the -1 and 1 on the bottom. So what that means is, as I go about solving this matrix here using some row reduction, the steps I take to solve for A and C are going to be identical to the steps I would take to solve for B and D. Their constant matrix is different, so I do need to make sure that I perform those row operations on both of these columns. But instead of having to do those same row operations twice, we can just do it once. So I can think of it as taking this matrix, and then let's augment this onto the side of it, and then we can row reduce, and we'll solve for A and C and B and D all at once. So that's where we're heading. So if I were to do that, I would get this 2, 1, -1, 1. And I'm going to have this one here, and then this one here. So this now is the matrix that we're going to row reduce. And when I'm all done, it will tell me the value for A and C and the value for B and D, because that's where these came from. So here's our value ultimately of A and B, or A and C and B and D. But AB, CD was our inverse. So what this means is when we use our row reduction, this matrix here is going to be our identity, or our inverse. And notice this was M, 2, 1, -1, 1, 2, 1, -1, 1. What this is giving us is a method of solving an inverse, no matter what size matrix we have. And here's what it is. You take your matrix, you augment the identity, you row reduce so that you have the identity now on the left, and whatever's on the right is going to be the inverse. So this is where you can pick up your pen or your pencil again, and we're going to start clean here, and we're going to row reduce until we get the identity on the left, and that will give us the inverse of this matrix on the right. So 2, -1, 1, 1, augmented with the identity. Now, as always, there are a lot of varieties of ways you can start this. I'm going to start in a different way. I'm going to start by adding row 2 to row 1 to get the 1 up here. But you could also switch these two rows and then negate, or you could cut this row by half. Any of these first steps are good first steps to take. My eraser just dropped. So I better not make any mistakes. So I'm going to take row 1 and just add row 2 to it. Now, yeah, I'm just going to speed through this, right? We know how to do this, hopefully by now. So I'm just going to speed through it. If you want to work it out and see if you get the same thing, feel free to do so. And we'll check at the end, see where we get. Okay. How did you do? Did you get where I got? So when I finished my row reduction, I got to, here's my identity on the left. And I get 1/3, -1/3, 1/3, and 2/3. So unfortunately, we have a bunch of fractions here, but it's how cookie crumbles sometimes. So we're going to say that M inverse is equal to that matrix, 1/3, -1/3, 1/3, and 2/3. Now we want to check this, right? We don't want to just kind of do this new process and assume this is correct. So what I'm going to do next is I'm going to multiply m by m inverse and m inverse by m, and we should get the identity both times. So I'm going to quickly do that as well, and then you can check your work. Great. It always feels almost like a magic trick every time I do this. I have faith in the process. I'm confident that this is going to be our inverse, and yet it's got all those fractions and nastinesses. And then when you multiply it through and you get these canceling fractions or these fractions that add up to 1, it soothes my mathematical heart. Just seems nice. So I did find that this checked out. Hopefully you found the same. And yeah, so now we know how to find an inverse. So I'm going to give you an example to try on your own. So here we go. All right, you all know the drill by now. So pause the video, work through this example, see if you can find the inverse for the matrix 3, 6, 2, 4, using the method we showed before. So augment this with the identity and row reduce until you get the identity on the left. And when you finish that, then you can unpause the video and you will see my work and we can compare, yeah? Cool. All righty, folks, how did we do? Did you get stuck on this one? You should have gotten stuck on this one. So if you got stuck, that's actually a good thing. So let's see why we might have gotten stuck. So I did a very similar technique for my first step. I subtracted row 2 from row 1 to get my 1 in the top left. And then I said, okay, to get a 0 here, I'm going to have to subtract twice the first row. So that's what I did. And that brought me to here. And when I got here, I was like, this is not so good, because now I have 2 zeros here. And when you have 2 zeros, that means there's no way to get a 1 back here for my identity, right? If I tried to introduce a 1 by bringing, a multiple of this row down, I would introduce a non-zero number here, thus defeating that last step we just took. So because there's no way for this to turn into the identity, this is a situation where A inverse doesn't exist. So I alluded to before, right? If I don't have a square matrix, then I can't find an inverse for it because the dimensions from the left and right will have to be different for multiplication. But here we have a case where we have a square matrix and the inverse doesn't exist. So, and it's not 0, right? We're used to like, okay, there's no multiplicative inverse for 0, la-di-da, but this is not a 0 matrix. And it's not even equivalent to the 0 matrix because its row reduction does not give us a 0 matrix. So we just have a matrix here, which is square, but is not invertible. So this is going to cause trouble for us. You can't assume that the inverse of a matrix always exists. So if the matrix is invertible, then we can apply certain techniques. But if it's not invertible, then we can't apply those techniques. So to close out this video, let's do one more little bit of exploration of using and applying an inverse if it does exist. So remember, in all of this, our goal is to find techniques for dealing with matrices so that we can solve systems of linear equations. So let's say I have a system of linear equations, right? So let's say I have AX equaling B. So A is our coefficient matrix, and X is all the, X sub i's, and B is all the B sub i's. Then, if A is invertible, so if we're fortunate enough to have not just a square by square coefficient matrix, but one that's invertible, we can do some stuff with it. So we can say A inverse times AX is A inverse times B. Now, when I'm multiplying both sides of this equation by A inverse, have to be careful. If I multiply it by the left on the left, I have to multiply it by the left on the right as well, because multiplication is not commutative. So we have to be mindful of these things. We can use the associative property to regroup on the left, but A inverse times A is the identity. And the identity times anything is the anything. That's from that lemma at the start of the video. So what this means is if I have a system of equations with a coefficient matrix that's invertible, I don't have to do row reduction to solve it. I can just take its inverse, multiply it by the column of B's, and that'll tell me the solution. So let's do an example of that and see how much easier and nicer it is than having to do, all of our row operations. All right, for this final example today, we're going to solve this system, mx equals the column matrix 13, 1, where m is the matrix from back in example 33. So in example 33, this was our matrix M, and we found its inverse to be this matrix here. So to solve mx equal to 13, 1, we can apply what we just did in that note and say that x is going to equal m inverse times the 13, 1. So all this is going to amount to is taking this matrix and multiplying it by this one this one's on the right. So this is going to give us 1/3, negative 1/3, 1/3, 2/3 times 13, 1. Now, when I'm dealing with fractions, I like to keep the denominator in place until I'm all done with my multiplication, and then I'm going to reduce. So so let's see, this is going to give me 13/3 minus 1/3. So 13 minus 1 is 12, so that's going to give me 12/3. And then I'm going to do 13/3 plus 2/3, 13 15/3. Well, we can see this is going to reduce because 3 goes into 12 4 times and into 15 5. So this is going to give us 4 5. There we go. That's how we solved the system. So you can see if we know a matrix's inverse, solving the system becomes much nicer. To check this, of course, we can multiply m by 4, 5 and see if we got back this 13, 1. Hi, folks, as I was checking my work, I realized I wrote m wrong, and I just don't want to refilm all of that again. So this should have been a 1. It was a 2 before. So let's check our work and make sure we got it right. So 4 times 2 is 8, plus 5 is going to give me 13. And then negative 4 plus 5 is going to give me 1. So this checks out, and we are good to go. So that's it for this video on defining an inverse to a matrix and our rudimentary attempts at finding the inverse of a matrix. We've been working with 2 by 2, so it hasn't been too strenuous on us, but if I had, say, like a 5 by 5 matrix, that would be kind of a pain to have to do all that row reduction. So our ultimate goal is to find some shortcuts to finding our inverses. But before we get there, in the next video, we're going to explore some properties of inverse. And because we've already seen one place where finding an inverse is helpful to solving our system of equations. So what are some other things that inverses can help us out with? And what are some properties of it? Just like we had properties of transpose and addition and multiplication and so on. So I'm looking forward to seeing you in that next video. And until then, happy mathing. So if we're fortunate enough to have a square, not only a, so if we're fortunate, why am I saying fortunate?